Okay, so our first speaker is Alexandre Minets, and he'll tell us about Cohomological Hall algebras and sheaves and surfaces.
Thank you very much for the invitation to speak. So, I changed the title a little bit, just because it's very much possible that I don't get to sheaves and surfaces part. So, I'll basically talk a little bit about cohomological algebras, what they are, give you a couple of examples, sort of give a feeling of what they look like. So let me start with the motivation part. And our point of entry be the Hilbert scheme of points. So let me just remind you quickly what it is. So for the moment we are working on C. So Hilbert scheme of points in A2 is just the is the moduli of ideals set the ring of polynomials variables, such that the dimension of the quotient, say, of n times 2, dimension of this quotient is equal to n. So you should think about this as n embedded points into the plane, like as an embedded subscheme. So we know it's a very classical result that this moduli, let me call this n in. So this is a smooth quasi-projective variety. And so, like, if you have smooth quasi-projective variety, one of the first questions we can ask ourselves is what are the cohomology of this variety? And the answer so the answer is given by another sort of classical theorem due to, I mean, it's called Gaussian formula, but I think the first proof was given by Alexandre. And the theorem says that, well, the good way to write down this Poincare polynomials of Hilbert schemes is to put them into generating series. Poincare polynomial in T, and sum over n. So this can be written down as a product. So we have this sort of nice formula, and so this part, it looks like created dimension of say some vector space which looks like ring of polynomials in my variable, say, such that the graded degree x, the degree of x, is going to be something like m minus 2m. So this is just sort of generating series of such things. And so there are several ways to interpret that this sort of formula exists. So first way, one could say, well, if you have something like symmetric power, looking at cohomology is basically sort of more or less the same thing as counting points if you were over a finite field. So it tells us there is some sort of decomposition into indecomposable pieces, and sort of indecomposable pieces are parameterized by these guys. So there is some kind of position in puzzles. Well, this is not exactly what happens here, but sort of verbatim. But if you look at this thing, you can sort of see that if I, for instance, here. So, for instance, I can consider fixed points on this towards action. So, I mean action on A to each space coordinates induces the action of the schemes. And so the fixed points are parameterized by partitions of n. Maybe let me just quickly tell you how it works. So, I mean, basically, fixed points are going to be ideals which are homogeneous with also rivals. So basically, your generators can be something like this: x, y. This is sort of a very well-known picture. So say you have an ideal generated by this guy, and this guy. Then sort of it will span all of those monomials, all of those monomials, all of those monomials, and this is going to be the Young diagram for a partition. This is sort of a very classical picture. So yeah, and then sort of you can say that partitions of n, this is sort of what is going on here. You decompose your n into different sets and you decompose them and then sort of have this thing. But this is like not the perspective that I'm interested in. So another perspective is that, well, what things have dimension of symmetric power symmetric space? So an example of such things are Verma modules. So another interpretation would be that this is a Verma module for some real. Say G equals to n plus T minus such that greater dimension and minus such that n minus is isomorphic to polynomials from a variable. And this approach can be made really precise. So this is sort of a theorem of Nakajima from 90s, which tells you that there is actually an action Heisenberg algebra on if there are some schemes. So this Heisenberg algebra just as a vector space is going to be something like C x E plus commutation. Something like that. So this is sort of a very nice and fruitful interpretation. But then sort of you can ask yourself, well, And this sort of tells you exactly that this is going to be the highest weight module or this algebra, which is the Fock space. But then, sort of, you can say, well, what is our Hilbert scheme of points? So this is basically, we can reinterpret it a little bit more geometrically, say that it is, say, torsion-free sheaves, coherent sheaves, on two trivialized at visualized at infinity, and with, say, rank 1, first Chern class equal to 0, second Chern class equal to n. And so you can ask, you can look at moduli space with Chern class bigger than that. So what if r is bigger than 1? Well, in this case, you also have formulas.
Pablo has a question.
Yep.
Is this really the Heisenberg algebra? What's the new Weil algebra to me?
Yeah, sorry. So hold on. Yes, you have sorry, xi delta I. Like you have actually infinitely many variables.
And you have
And then you have delta ij. Okay. Thanks. So yeah, because otherwise, like dimension wouldn't match to begin with. So yeah, in this case, you have formulas. Also have formulas which describe the dimension for dimension of cohomology for polynomials. But the sizes of groups are going to be bigger. So somehow there should be some bigger algebra in place with that. But
I missed what R was.
Huh?
You think R equals 1, but I missed what R was.
R is the rank of my sheaf.
Ah,
It's maybe torsion E, and then you put R rank E, first Chern class E. So, but the dimensions are bigger. And this suggests there are bigger algebras acting on these spaces. It means it has more generated. I don't know, like in a sense that say SL to affine is bigger than Heisenberg algebra. It's like
Heisenberg algebra itself is generated by one element.
yeah.
It's like rank 1.
Well, no, it's not generated by one element. Sorry.
Well, in some sense, not as an algebra.
You mean as a vertex algebra, or like by one field? Yeah. Yeah, maybe I mean that like literally, like you can put great many algebras and great dimensions eventually bigger sort of dimension by dimension. That's or maybe okay. Maybe let's put it this way. There are some bigger algebras, which means that there is some algebra which is going to contain this, but there are going to be more operators. Maybe this is the best way to say it. So anyway, like the sort of the natural context, so where those algebras appear, is this is going to be some cohomological Hall algebra. And I'm going to explain to you what this is, what this sort of notion is. But first, sort of motivate a definition which is a little bit technical. I will start with another thing which is called Ringel-Hall algebras. But before I continue, do you have any questions? So in this part of the talk, and only in this part of the talk, I'm going to work over a finite field FQ. So let's Q, and let me fix C, which is going to be a bilinear category, which satisfies the following conditions. So first of all, for any two objects, I ask that all the high extensions vanish, and then I ask that Holmes and first extensions are all finite, which means that the dimension is finite since we're working on finite. So examples of such categories are, we can take representations of a quiver, say finite dimensional representations, or coherent sheaves over some curve where x is smooth objective curve over Q. So smooth assures that you don't have those guys, and projective assures this condition. So definition. So Ringel-Hall algebra, which I will denote HCC, is defined as follows. So as a vector space, is going to be just C-valued functions, complex valued functions, on a set of objects of our category. And here, so with finite support, or complex support, and here, I really consider this as a set. Like, there is no topology, there is nothing. And the product should can you read here? Maybe I'll pass it here as well. So the product is going to be defined by the following correspondence. Well, you can take objects in a category 2 times in one time, and here you can put two set flags, which is going to be flag 2, just the set flags like this of objects, and then the maps are going to be 1, 2 maps to E1 over E1. Let me call them Q. So what you can do if you have two functions on the set of objects, you can take their sort of product, you can pull them back, you can push them forward, and because of this finiteness condition, the fibers of the snap are actually going to be finite, so there is no problem with it. So product is given by f g is going to be just or in a more specific fashion, which is going to be more useful for examples. So any object in my category, I can consider as a characteristic function. Say in HC, which is going to be just 1 on this object, 0 everywhere else. So these functions will also generate this as a vector space, and the product. So if you unwind this definition, is going to be just sum over C So basically, you just take extension, count extension. How many times C can be written down as extension of A. So proposition, this is an associative product. Which is not that hard to prove. You just need to notice that basically associativity boils down to the fact that you have sort of like a three-step flags, and sort of associativity boils down to some sort of base function. So let me give a couple of examples how those things look like.
So just to be explicit, you're actually considering these as sets modulo the obvious notion of isomorphism.
Yes.
Like that count, you're not counting A prime such that it happens to be isomorphic to A, but counting those supplied with isomorphisms to A when you define the product. Otherwise, unless you mod out by
I think here, yes, this is something you should pay attention to. But I think here, yes, they're not split. Here they're not split into isomorphism. Just sub-objects such that there is isomorphism.
could you mod out by the
I think you want to take your C's up to isomorphism. But then
Yeah, ob really means this set of isomorphism classes.
I just
Yeah. Well, it's objects in C. Yeah. So say up to isomorphism. Yeah. That's, and like everywhere when I write this, I actually mean up to isomorphism.
but so this is like I apologize, it's like a totally minor complaint about the notation, but as written that's not correct, is that right? You could redundantly count many such A prime, you still need to mod out by something. And my claim is to mod out by the right thing, we'd like to write those diagrams of supply group things and then mod out.
No, I consider those like I don't consider this as a map. I consider this as a sub-object.
Oh, I see. Okay. Thank you.
Yeah, the condition is that there exists an isomorphism.
Yeah, there's a notion of sub-object where you don't need to specify it.
Yeah.
Sorry, can I ask, why do we need that higher extensions range?
That's a good question. In what I'm going to say, we don't. But somehow the point is that those algebras, they admit an actual coproduct, which is going to be just go that way around and pass to some sort of condition. And the point is that if you don't have higher extensions, then you can like tweak the definition a little bit so that it becomes a algebra. And if you do have higher extensions, you cannot. And somehow we really want to obtain. I mean, you will see in the examples that what we obtain is it's going to be something that we expect to be by algebra. But yeah, in what I say, it's really not going to be important. Just a quick remark. No, yeah, it's remark no. So the easiest example is just high-dimensional vector spaces over a cube. Here, the objects are just parameterized by integers, and if I take, say, ka 1 m times 1 n, well, what is it going to be? Well, we will have only one summand, which is direct sum of the vector spaces, and then this number of sub-objects such that it's isomorphic to this one and the quotient to this one is going to be just number of points in the first number of points in the Kostanian, say, m or n continuing notations. And you can see that this thing, it doesn't depend on the order in which you multiply. So actually from this you can deduce that fact is going to be just polynomials in one variable, where e, say, let me say 1. So easy enough. So the second example is going to be representations of this simple quiver. So once again, we know what the indecomposable representations of the quiver are. So we only have 3 indecomposables, which is going to be just this thing. These are dimensions. This thing, and then this thing. Let me call them S1, S2, S2. So, so representations of this quiver, we can decompose them with respect to the dimension. So, to the dimension vector. So, if you look at representations of dimension T1, well, if you just look at this thing, it's pretty clear that you can have only 2 such representations. You can either have T12 plus S1, or S1 plus S1 plus this. To have this thing, and now I'm going to ask myself, well, I can consider products like so. So I can just take product of characteristic function of S1 and S2, so 2 times S1 and 1 times S2 in 3 different ways. I can basically put S2 either here or here or here. Let me abuse the notation a little bit, and instead of 1 of something or some object, write just this object. I hope it's not very problematic. So I can write down those 3 things. And all of them, by dimension argument, are going to be a linear combination of those 2 guys. Which means that there's going to be a relation between those things. There is a linear relation. and up to small generalization, which is not going to be important for later, but let me just, to be precise, say what you need to put here. Like here, actually, in order for this to work, you need to put so basically the other characteristic of home. And so with this renormalization, the linear relation is going to be just S1 square S2 minus 1 half S2 minus 1 half S1 plus S2 squared 0. And I think many of you know this relation. This is precisely one of the relations in quantum SL2. It's a relation between E1 and E2 in EQ. So this is not a coincidence. So theorem due to Ringel-Green is that so let's see the representations of Q and G. Let G be the Kontsevich-Soibelman algebra, which corresponds to the underlying graph of our query. Let's say no loops. Q has no loops. Then you will have an embedding of the positive part of this Kontsevich algebra. So the difficult part is to show that it's an embedding. Like the relations we just need.
So the Q in the top line is a Q like FQ, right? But the Q in the bottom line is...
Yes, sorry. Let me say eta, where eta is Q of half. Then this is correct. And one can upgrade this theorem to a theorem about not just the positive half, but the whole thing. Because as I mentioned before, whole algebra has a natural coproduct, and you can recover. So if you can upgrade this Newton part to the Borel, and then you can actually upgrade this into embedding of Lie algebras. So you can recover the whole quantum group and not just the positive part. And let me just mention two more examples without doing any computations. So another example is Newton representations of such Kruger. In this case, we will have polynomials in infinitely many variables, and it's basically due to the fact that these representations, they have Jordan normal form. And last example is Q-Schiffmann P1. Then it's a theorem due to Kapranov that this thing is going to contain here somehow the co-kernel is also rather, so if you can express it, it's not a big problem that it's not isomorphism. By the way, here it's iso in type AD, infinite type. So here you will have positive part. How do I put it? So loop for the positive part of SL2, And what I mean by that, I mean that sort of when you can sort of draw sort of root system for your SL2 affine, something like this. And normally, like when you take standard Borel, then the standard Borel will sort of capture those roots. And this is not in here. We mean a non-standard Borel, which goes like this. This is just what happens. So, after giving you a bunch of examples and using up more than a quarter of the time, I'm going to finally pass to cohomological algebras. Define what they are. We know that this category is directly equivalent to the category of representation of current computer, and basically the point is that if you take Greenfield double of your whole algebra, it is supposed to, like this object is supposed to be a derived invariant. I'm always confused as to like what part, like in what generality the statement is proved, but like in this case it's certainly true, and in sort of most sort of combinatorial cases it's true. Well, let us pass to cohomological version. Are there any other questions? So, this is just some algebras, but they are not going to act on cohomology square Hubler scheme or something, you know, on the node, because basically they are not cohomological objects. So, if you look at this definition, the definition of this product, so one easy way to sort of make it cohomological would be to say, okay, let us consider those as not as sets with actual spaces or stacks or something, and listening to, and then you just do pull pushing cohomology. So from now on, my ground field is going to be C, and for the time being, let me just restrict myself for ease of exposition. For the moment, I will consider only category representations of Krivers. So, definition, cohomological algebra of Q is going to be the formal homologies of Q, where this is the stack, the arc stack, equipped with the product being also given by this pull push, but in cohomology. So I have a couple of remarks. So when I say arc instead, you really shouldn't think about, I mean, if you don't like, you shouldn't think about sets. What you should think of is that, like, rep Q, at least with fixed dimension, is going to be a quotient set with just some vector space over a reductive group. And therefore, like, homology of your rep Q is going to be some sort of coherent. So you can just think in terms of coherent homology. And the other remark is that, well, this definition works well, just because sort of this map is certainly going to be proper, so you can put forward, and then this map, well, it's going to have a fiber like over AB. The fiber is going to be something like x1 AB over home B in the sticky sense. This is statement bundle, and note that this thing has a constant frame, so this step is smooth, and we can just pull back without a problem. It's going to be basically nice and works. All right.
Isn't it more like x1
It might be. It depends on my notations. Yes, x1 b. Thank you.
So do you still have the loopless assumption on the quiver or any quiver?
I don't think I do. No. Here, this assumption I only use to say this theorem, because basically, if you have quiver with loops, it's not going to be custom algebra. You have to introduce something else, and I really don't want to do it here. All right. So once again, this is going to be an associative product by the same trick. And one might think, yeah, it's basically the same thing. We'll get some version of quantum groups, or universal enveloping, because it's not clear what the quantum parameter is here. But it's not actually how things work. Maybe let me keep this just because of the diagram. And let me just show it with the following example. Basically, this example that I just raised, where I take Q, which is just a point. So what happens in this example? Well, first of all, so representations of Q. Once again, these are going to be stacked spaces. And as a stack, it's going to be isomorphic to the union of VGLN for all n. So already, when we take cohomology, so this thing is going to be basically cohomology of this thing. It's just symmetric polynomials. So it's going to be C x1 xn symmetric n for all. So first of all, for this theorem, from this theorem or from the example that we considered, we should get something like, we would expect that we get something like, universal enveloping of positive part of SL2, which is just commutative. We see that this space is too big to be that, but sort of second guess would be, well, it looks like some sort of affinization of the same thing. And it's actually not going to be that either. Let me just say that it's a guess. So maybe it's isomorphic to something like U SL2 hat plus, something like that. Note that positive half is still commutative. And let me just show you that the product here is not commutative. So let us just make a very simple computation. So let me take x1n and x1n inside homology of EGM, saying for n equals to 1, and compute this product. So how do I do that? Well, basically by definition. So let me, for the moment, write H for GM plus GM. It's contained in Borel, it's contained in G. GL2. So
I have a question. So so you wrote this direct sum of symmetric. Wait, I'm confused that you're taking x1 to the m and x1 to the n. Oh, I see. So we're taking like the n equals 1 piece of that.
Yes, yes, yes,
Because
yes,
that's
yes.
to be
So
symmetric.
this is going to be
Got it.
Cx1 if you want symmetric one, but this
Yeah.
doesn't.
Okay.
So yeah. So let's write the diagram. The diagram we get is the usual diagram like this. BH equals to BB equals to G. Sorry for the fact that B means two things here. And now all of us know then that in cohomology this thing is going to be isomorphism. Or cohomology. So basically all of the product is going to be contained in this map. And what we can do, we can sort of take fiber product with G, or I mean, we can base change with respect to this map, compute everything here, and then take it to variant cohomology. So when I do this, what we obtain, like this map on the right, is going to be this point, and there I'm going to get P1, and then I have to get G variant cohomology. So and what this map is going to be? Well, P1, let me write this Q here. Here we have a coherent cohomology of point. So one thing that we can do, I mean, is the usual thing, we can compute it using localization. So basically, we consider the action of maximal torus on those things. Here does nothing, and here the fixed points are going to be 0 and infinity. So let me, I don't know, 0 and infinity. Take one is going to be here. So here we take it back. Cohomology.
So do you need to write G there or B or T on the
Here?
yeah, in coherent cohomology?
I mean, like, you need to write T, but then I'm being sloppy representation. Here, normally you write T, but then you know that G coherent cohomology is the same thing as Sn invariant part of T coherent cohomology. So I just write G and sort of. So now you could say, okay, I just do this and this. This diagram does not commute. We need to insert some sort of Euler classes of conormal bundles to those guys here. And so the result is going to be x1 m xn. So we are going to have following. Here this is the character of the tangent space at 0, and this is the character of the tangent space at infinity. It's very much possible that I this is the other way around, but anyway.
Everyone became an x2?
Because sort of like x1 is here, x2 is here, x1 like
Maybe
what
y1 would be better than x2 because it's like
no. What I'm trying to say that here you only have x1, here you also only have x1, but then when you consider them together inside GO2, they will be different variables. It's going to be x1 and then x2, and then sort of in the middle of us. Here I have to write x1, but then when I go through all this thing, it's going to be x1 and x2.
Mm-hmm.
So, but at the end of the day, what's happening is that we get so the minus we get this, and you can see if we switch m and n, the sign changes. So this thing is not commutative. So this guess is wrong, it's not true. However, However, if those denominators were something like this, or if you had no denominators whatsoever, then it would be alright, because then you would not have no sign, and then it would be commutative as one would expect. And so the way to sort of get this modification is to consider cotangent bundle theory. So basically, what I do, I take T star of this and this, and I take conormal bundle. So I take T star H, T star G. Here I take normal of DB over G. And now let me just look at this map. So what happens here? So we know that I'm going to be once again sloppy with the shifts because So I'm going to just omit all the cohomological shifts, like direct shift. So this is going to be G star on G, and this thing, as it was computed in previous lectures, this is normal G is going to be B star over P. And now you see that now when I do the sort of map, as before I will have P1 because sort of I made BD to be G, but also I will have additional sort of now when I localize, I will get conormal bond. I will have to localize both here and here because now I have like this trivial, and the difference in the other classes is going to be something like n star minus n star minus, and sort of this thing has weight x1 minus x2 or the other way around. So when I sort of plug it in here, I will get something symmetric. Like I don't want to screw up this pattern. So it's either going to eliminate those. Yeah, it's just going to cancel those things out, and you will get just something. So get commutative product. So the upshot is that in order to get say UG, need to take star term. So what happens when we take cotangent term? And badly out of 10, not yet out of 10, in the very near future. So what is star this thing? Well, this is going to be just representations of pre-projective algebra. So you could say, okay, let us consider just sort of the same story from this pull-push diagram, but we replace our pure with pre-projective algebra. A representation of pure with representation of pre-projective algebra. Well, the fact of 5 is that this thing has cohomological dimension 2, which means that it has non-trivial second best. It's also clearly out category, but it's not important. And so, like, pullback is not clearly defined anymore because this thing is going to jump in dimensions. So you have to do something. Like, it's not clear if pullback is going to be well defined. And so what we can do instead, well, not instead, so let me just write this down. So this thing, is not smooth. However, we know what the fibers are. So the fiber is going to be like this. So okay. So let me say the following. Let me just throw the following back, which is going to be something. So let us consider our home E1, E2, where so let's say we pick a couple of representations here and consider this complex, and let's shift it by one. Now we know that in this category we have home x1, x2, and nothing else. So one could show that this thing can be written quasi-isomorphically as a complex of vector angles of length 3. And -1 is integer -1, 0 and 0, 1 and so on. Now, so what we can do, well, we can do two things. So let me ignore this thing for a second. So we can write down the following diagram. So we have rep spread. This embeds into the total space of E1. Have a map from total space 0. And what do we have here? So here we will have just the kernel of this map, and like I consider everything like equivariantly with respect to E-1. So I just don't write that I quotient everything out like this. So what we will have, like the kernel is going to be precisely x1 v1 v2. So if you just write this down set theoretically, we are going to get our flag 2. But this is not a Cartesian diagram in the sense that you cannot do pullback. You cannot do base change. So once again, we want to do pullback like this, and we can do pullback here. And now the point is that if I take this in direct sense, derives product, then this map is going to be well defined. So basically what I'm saying here is that we replace these two-step flags with, we equip them with some derived structure. And so now we have this map. And we can also, when you do push forward, it's not going to matter. So we basically, now this thing, if you replace this by this, it's going to be well defined, this is going to be well defined, and we once again get associative algebra with a little bit of work. You have to check that everything sort of everything works well. At least give you associative work. And this is not something kind of sensible abelian category of cohomological dimension 2. And when I say sensible, I mean moduli over some sheaf of algebras on some smooth variety. Some smooth cork variety. It works for any other category of cohomological dimension. And still have 5 minutes. Okay, so maybe let me conclude with a couple of examples. So, let me define this thing. So the first example, the main example, original, what is the following. Let us say Q from a fever. Then T star Q is going to be the same thing as CXY modules of finite length. And then, and also let me replace, okay. So first of all, okay, so there are two statements. First of all, this cohomological algebra of this state Q, the sum, and as well as higher rank moduli. And somehow, in a certain way, like this thing is going to be like the limit, like dimension, like create dimension-wise limit of those things when rank goes to infinity. So this is sort of the correct thing. And now let me just write COHA on the same thing, where I just do the same thing, but I replace cohomology case here. So this thing is now under a couple of different names. Let me just write some of them down. So this is this, the key theoretical algebra of commuting varieties, because basically here we will get commuting varieties. Then it's known as elliptical algebra. Say positive half, because it's going to be isomorphic to a certain part of whole algebra, usual algebra from previous part on an elliptic curve. Other name is known under it's quantum toroidal GL1. Because basically you can think about Heisenberg algebra as affine GL1, and then when you do this, as we discussed, it looks like affinization, so it's quantum toroidal GL1. So another, to take back to a couple of thoughts that we had, so it's a limit of spherical DAHAs in type A. It's also known as Holmfei's kind algebra for torus. Also, it's known as, I guess, Fagin-Adesky shuffle algebra. Yeah, I think that's enough. No, but
so you always have equal parameters in these lists?
Actually, I thank you. So I skipped the parameters part. And yes, you're right. I mean, it's not. Yeah, here it's not. Okay. So I need to say that here I actually want to consider equivalent cohomology, equivalent K-theory, with respect to two-dimensional torus which acts on A2, or if you want on two loops that you're going to get here. And this thing is not literally the same thing, but you have to set Q equal to T.
In the K-theory called construction, you have the two parameters and they correspond to the two parameters.
Yes.
That's the
And okay, so let me maybe end with last sentence. Is going to be another example. So another example, you would ask yourself, what happens if you consider some surface? If you consider a cohomological algebra from surfaces. So for instance, of of these searches. Why T star P1? Because we have a good sort of idea what it should be, sort of in keeping with our philosophy, because we know that usual full algebra of P1 it is affine SL2. So here we will get something like double affine SL2 or GL2. I mean, this is sort of yeah. And so the point is, this is say work in progress. For T star P1, it's almost clear, but in more general sense, it's work in progress. So if you take AD resolution of AD singularity, let me call this as gamma, then say alpha as gamma is going to have inside U. So G gamma is the finite type, the algebra, like say simple Lie algebra. You take double optimization or like toroidal version, and here I put dots. Means that normally you will have at least one quantum parameter, but sometimes you have two, just because on the resolution of AD singularities, sometimes you have action of one C star, and sometimes in type A you have action of two C star. This is work in progress. And I think stop here.
Is there a quick question?
So this cohomological algebra before that wasn't commutative.
Yeah.
So, but is it super commutative?
I mean the so for one vertex thing.
Yeah. Then it's an example.
Yeah, in my example, I think. What is it?
Where's all your x's degree 2 anyway?
Huh?
Where's all your x's degree 2 anyway? Because they were cohomology with DGLA.
Yeah.
So, still not commutative.
Yeah. Yeah.
No, I mean if you put degree like dimensional.
I have to check. I don't want to wait. So let's leave it at that.
Increase number from some other consideration.
Yeah, I think it's going to be super cool. Yeah, it's going to be like yeah, it's going to be like universal. It's some sort of like what Kontsevich-Soibelman called an instance of Boson-Fermat correspondence. So it's instead of universal enveloping of Heisenberg, as in like here, this is going to be universal enveloping of Clifford, I guess. So it's good, yeah.